All right, so we're going over conservation of mass, which we already know. Okay, we're going over balancing, which we already know how to do. This is just kind of the notes on it, so you kind of see how that's arranged. And then we'll talk a bit more about the predicting the product stuff, do a few more practice questions on that, and then we'll be ready to set up for the pre-lab. Okay, so first thing, we need to understand that the amount of atoms in the reactants is the same as the number of atoms in the products. Right? When we balance a reaction, we're making sure that that is the case. Okay? Because we have to do that, otherwise we have disobeyed the law of conservation of mass. We have created matter or we have destroyed matter, okay? And we can't do those things. So that is the whole purpose of using coefficients to balance the equations, okay? Which, like I say, we've been doing already for a couple of weeks, and you guys are pretty good at it. All right, so in a reaction like this, obviously, or in any reaction, mass has to be conserved, okay? So in this reaction here, on the reactant side, we start out with 2 molecules of hydrogen gas, each molecule containing 2 atoms, so 4 atoms of hydrogen in total, okay? 1 molecule of oxygen gas containing 2 oxygen atoms, okay? And when those things react, we end up with 2 molecules of water, okay, each molecule containing 2 atoms of hydrogen and 1 atom of oxygen, still giving us a total of 4 hydrogens, 2 oxygens, 2 oxygens. Okay, that's what those prefix or those coefficients are for. Okay, just to make sure that we have the same amount of everything on both sides. All right, if I'm looking at this picture here, okay, so this first picture A is the reactants of a reaction. All right. In the reactants, we have 2, 4, 6, 8, 10 red atoms, and we have 2, 4, 6, 8 yellow atoms. All right. So which one of the diagrams of products there shows the law of conservation of mass being obeyed? Which one? There's 2, 4, 6, 8, 10 red ones in this one, but there's only 1, 2, 3, 4, 5 yellow ones. Okay, did I destroy some matter in that one? Okay, obviously C is not right. There's just way less stuff in C than there is in A. Okay, on this one though, I've got 2, 4, 6, 8, 10 red ones and 2, 4, 6, 8 yellow ones. Is it okay that some yellow ones are left over? Yeah. Okay. In most reactions, we don't usually show this. Okay, we only show what reacted. But in a lot of reactions, you're going to end up with a little bit more of one reactant than you needed to complete the whole reaction. Okay, your limiting reactant is the one you have less of. All right, so there's always going to be a little bit of one of them left over at the end because there just wasn't enough of the other reactant for it to go with. But it'll still be there. It doesn't just disappear. Okay? But when we write a reaction, we only worry about the stuff that's actually going to react. Okay? All right, so when we're balancing chemical equations, rather than go through this, we've simplified our balancing rules. Okay? For all reactions except combustion, we start with the biggest what? We want to start balancing reactions except for combustion. We start with the biggest charge. Well, okay, the charge can be the tiebreaker, yeah, but the biggest number other than that, right? So if I've got 8 sulfurs and everything else is like a 2 or a 1, I start with 8, okay? And I put in the 8 and I start balancing from there. It's always best to go with your biggest number, okay? Because it's usually going to influence the other ones. And if there's a tie, then we go with the bigger charge. That's the tiebreaker. All right. If we're using combustion reactions, obviously they have their own 2 special rules. Okay, we balance them in alphabetical order, not the biggest number, but the alphabetical order, and the rule of 2, which only applies if we have an even number of carbons. Okay, we've greatly simplified these rules down to that because that works. Okay. All right, so we're going to skip over that stuff. All right, here's what I want you guys to try. I want you to try the first 3 reactions there. Actually, you know what, I'll scroll up just a little bit to get the 4th one on there. Okay, try those first 4, okay? So remember, the steps went like this. I identify the type of reaction, then I use that pattern to predict who goes with who, and then in my products, I check for special elements, I drop and swap ionic compounds, and then I balance the whole reaction after that. Okay, so type, pattern, okay, drop and swap, check for specials, balance the reaction. All right, I'll give you a little bit of time on those, then we'll go through them together. All right, so for our first two here, okay, we've got calcium reacting with oxygen. So two elements reacting is what kind of reaction? Synthesis reaction. Okay, so in a synthesis reaction, the pattern says these two things go together to make a single compound. So Ca with O. All right, and we said yesterday that I might try and trick you on a quiz by putting the non-metal first to see if you remember that when I make an ionic compound, the metal needs to be written first. Okay, so we've got this being a -2, we got this being a +2 because it's an ionic compound. We got to drop and swap. Looks good, so I don't have to do anything else with it. There are no special elements, so that box is checked. And now I've got to balance the whole reaction. 2 oxygens in the reactants. Now I got a 2 here. Okay, I got to go back over here and make sure I got 2 calciums. Now the reaction is balanced. Okay. All right, what kind of reaction is the second one? We've got magnesium sulfide as the only reactant. Yeah, it's a decomposition reaction. So it's going to break down, according to the pattern, into its 2 elements. Now, something we always have to watch for with a decomposition reaction is the production of what? Special elements. Yeah, I'm going to make 2 elements here. One of them could be special. Both of them could be special. Okay? There will never be a case where neither are special. Why? What would you have to have bonded together to get no special elements? 2 metals. Do 2 metals ever bond to each other? No. Okay. All right. So we would have Mg. Okay. So we would have no number on that one, but sulfur is the most specialist of all the specials. Okay. It is an 8. All right. Now I've got to go back and I've got to balance everything. So I got 8 sulfurs on that side. Now I've got 8 sulfurs in the reactants, but that gives me 8 magnesium. Okay. Now I've got 8 magnesium, and we're good. Okay, let me go to done number 3. All right, let's look at that one too. What kind of reaction is that? Combustion reaction. Okay, do I need to figure out the products or should I just know them? This is one I just know this, okay? The products of a combustion reaction are always the same 2 things, carbon dioxide and water. Okay, do I need both balancing rules? No, 3 is an odd number, so I don't have to apply the rule of 2. Okay, now I'll balance alphabetically. 3 carbons, 3 carbons. 8 hydrogens, 4 times 2 is 8, and now I can do the oxygens. 4 times 1 is 4 oxygens there, okay? 3 times 2 is 6 oxygens there, 6 plus 4 is 10, 5 times 2 is 10. Okay? Questions on the combustion one? All right, how many people have done number 4? Okay, let's do number 4 and then we'll look at some other stuff here. Okay, so on number 4, what kind of reaction is that? Okay, double replacement reaction. So in a double replacement, how do I know that this is ionic?
Hydrogen's first.
Hydrogen's first. If hydrogen's first, it's acting as a metal. Sometimes that throws people off, okay? Because they're like, oh, hydrogen's a gas. Yep, it is, but it's also a metal when it's listed first. Okay, so these are 2 ionic compounds that are reacting with each other in a double replacement reaction. Our pattern for double replacement is that the metals are going to switch places. Okay, so that means that sodium is going to end up with chlorine and hydrogen is going to end up with hydroxide. Okay, did I just make 2 new ionic compounds? I did. Okay, I mean, I'm writing water like it's ionic. I saw people nod no, and yeah, you're kind of right. Water is molecular, but lots of times it behaves like this, and we write it like this. Okay, so this is a +1, that's a -1. Is that compound okay? Yes. Okay, this is a +1, this is a -1. Is that one okay? All right. So I had 2 ionic compounds there. So this something that had to do with some of the stuff in the properties of compounds lab. What would the pH of this compound likely be since it's ionic and hydrogen's first?
Acidic.
It would be acidic. Okay? Anytime you have an ionic compound with hydrogen acting as the metal, you have an acid. anytime you have an ionic compound with hydroxide acting as the nonmetal, you have a base. Okay? When you mix an acid and a base, what do? They neutralize each other. If you have exactly the right amounts, they would completely neutralize each other. All right? So in any acid-base reaction, neutralization occurs, okay? And that's always going to produce water and a salt. In this case, actual table salt, okay? But any other ionic compound. Okay, so anytime you have an acid and a base reacting, you're going to get water, and in that water will be dissolved an ionic compound, a salt of some kind. Okay, that sort of makes sense? All right. Now, I used to give everybody like a copy of this flow chart, but I found people got way too dependent on it, and it makes it look more complex than it needs to be. Okay, we kind of just have these rules now when we're predicting that say, if I know the pattern, and this just kind of help people with the pattern, okay, if I have a synthesis reaction, I put the elements together. Well, yeah, because that's what a synthesis reaction does. And then I balance. If it's a decomposition reaction, I split the compound and write the elements. And I check for special ones, and then I balance. Okay, if it's a combustion reaction, well, we had a whole big thing with them. Okay, I balance in alphabetical order. I put a 2 if it's even, and then I balance. Okay, for single replacement, I check the lone element and I swap it for the thing that's in the compound that it's like, and then I swap and drop and check for specials and balance. Okay, so people just end up getting too reliant on that, so I stopped giving it out because you guys already know the patterns. Okay, you can figure those things out. Come on now. All right, let's have you guys try 5 through 8 there. We got a couple of different ones in there. All right, so the first one, we got beryllium reacting with iodine. What kind of reaction? Synthesis reaction. All right, so they're going to go together. And when they go together, they're going to make an ionic compound. Okay, this is a -1, this is a +2, so we're going to have BeI2. That works out nicely because now the reaction is balanced. Okay, 2 iodines on both sides, 1 beryllium on both sides. Okay, sometimes they're that simple. All right, number 6. What kind of reaction is that? We got potassium reacting with iron 2 oxide. Single replacement. Okay, so the pattern for single replacement is that the element replaces the part of the ionic compound it's like. Since potassium is a metal, it's got to replace iron, which is the metal in the ionic compound. So we know then that iron ends up alone, and that potassium ends up with oxygen. All right, now, single replacement reactions are the ones that have the most nitpicky little details to watch out for. They can produce special elements. Did this one? No. Iron's not special. Not in like the molecular element special. It's special in that it's got more than one possible charge, but it doesn't make it a 2 or anything when it's by itself. So no special elements. Okay? But they always produce ionic compounds, so those have to be dropped and swapped. All right, so K2O. All right, so I've checked for special elements. There weren't any. I dropped and swapped the ionic compounds. Good there. Now I got to balance the reaction. Everything's balanced except potassium. That's fixed. Now the reaction is balanced. Okay? All right, what kind of reaction is number 7? Double replacement. Okay, so in a double replacement reaction, I've got to swap the metals. Okay, that's how the pattern works for that. I need to make 2 different ionic compounds, and the best way to do that is just to make the metals have different partners. So that means magnesium will end up with sulfate, and copper will end up with chlorine. Okay? No special elements are produced, so I don't have to worry about that, but I did make 2 new ionic compounds that both need dropping and swapping. Okay, so for this one here, magnesium's a 2+, sulfate's a -2, so that compound's fine. I could write brackets if I wanted to, right? And then for copper and chlorine, what do I have to remember about copper?
More than one charge.
It's got more than one charge. Okay, if this was written out in words, I would know what that was from the Roman numeral, but it's not. So what I've got to do is go back to the reactant side and see what charge did copper have over here, because it'll have the same one over there. Right? It's with sulfate, which is a -2, so that means it's got to be a +2. Now I can go back over here and go, all right, +2, -1, we're looking at CuCl2. So there's a little, sometimes you gotta watch for that in a double replacement reaction. You could have multivalent metals, and you'll have to investigate back to the reactant side to see what their charge is. All right, what kind of reaction is number 8?
Combustion.
Oh, sorry, I didn't balance that reaction, did I? Yes, I did. It's already balanced. That's lucky. Okay, so we got a combustion reaction for number 8. What are always the products?
Carbon dioxide and water.
CO2 and water, always. Okay. All right, no special elements, no swapping and dropping, but 2 balancing rules. Do I need them both? On this one I do. 4 is an even number. All right, so I'm going to start with a 2 here, and then I'll balance alphabetically. 2 times 4 is 8. Now I have 8 carbons on both sides. 2 times 10 is 20 hydrogens. 10 times 2 is 20 hydrogens. Now I can do the oxygens, they come last. Okay, 8 times 2 is 16 oxygens there, plus 10 times 1 is 10 there. 16 plus 10 is 26. 13 times 2 is 26. Okay, we've done 2 combustion reactions today. We have done those same 2 combustion reactions like 4 times each, okay, already, all right, this semester. I never get bored of them. Maybe they'll show up somewhere else. Okay. All right, last one here, and then there'll be last 2 here. Okay, let's try those ones real quick. I'll give you about 2 minutes on those, and then there'll be one that I want to show you that has one little thing that we haven't covered yet. Okay, so a couple minutes, and then we'll talk about those 2. All right, so for number 9, okay, we got rubidium phosphide. It's a decomposition reaction, so it's simply going to break down into rubidium and phosphorus. What do I need to check for? Special elements. Do I have any? Yeah. Phosphorus comes as a 4. Okay, now that I know that, I can go back and balance. I put a 4 here and a 12 there, and everything will work out. Okay. Now, for our last one here, this is like as nitpicky as a double replacement reaction can get. Why?
There's more metal.
Actually, there's 2 metals. This is cobalt. Yeah, sorry. It looks like carbonate because I made the O too big. My bad. So this is cobalt. This is lead. They're both what kind of metals? They're both multivalent, right? They both have more than one possible charge, and I got to figure out what that charge is before I can drop and swap the products on the other side. Okay, so there's tons of little nitpicky details I got to be mindful of when I'm doing this one. Okay, so it's double replacement, so we're going to swap the metals. So cobalt, which I wrote very poorly here, guys, sorry about that. Okay, is CO with Cl. Okay, and lead is going to end up with phosphate, PO4. Okay, now I don't know what the charges on cobalt and lead are yet, but I will figure them out. Right? So phosphate is a -3, and there are 2 of them. That's a total of 6 negative charges. So I've got to get 6 positive charges from 3 cobalts. That means each cobalt is a +2. All right, so this is a +2, that's a -1, COCl2. Okay, then I'm going to go back over here and do the same thing for lead. That one's a bit easier. Chlorine's a -1. There are 4 of them, so that means that lead's a +4. Okay, so +4 and a -3. So 3 goes here, brackets with a 4 outside of the brackets. Okay. Cumbersome? Yes. Okay, double replacement reaction that's got lots of multivalent metals, a pain in the neck. Okay. All right, now that I've done all that, now I can balance. 4 is the biggest number, so I'll balance it first by putting a 2 here. That's going to give me 6 cobalts, so I'm going to put a 6 here. That's going to give me 12 chlorines. A 3 here takes care of that and balances my leads on the other side. Okay? All right, one more reaction, but it's got a trick in it that we have to also be aware of. Single replacement reaction like this one. Let's say copper reacts with sodium chloride. Okay, it's a single replacement reaction. We know that copper has to replace the metal, which is sodium. Right? So sodium is going to end up by itself, and copper is going to end up with chlorine. What's my problem?
You don't know what charge copper is.
Yeah, we don't know the charge on copper. Copper can be a 1+ or a 2+, and because it was an element going in, and elements have no charge, I have no way to figure out what the charge on copper is in this situation. And it comes up sometimes with single replacement reactions. So what do I do in that situation? Well, your periodic table is arranged so that the charges are listed from left to right in the order they come in. So like the volume that they would come in, or the percentage they would come in. Okay? The first one listed is the much more common of the two. All right? And usually it's like this one's 90% and this one's 10. Okay? Or sometimes it's like 98 and 2. Right? So that second charge, while it's there, is not nearly as common as the first charge. So if we're not told otherwise, we go with which one is more common. In the case of copper, 2+. Okay? So that's what I do in that situation. It comes up, we have to know what to do, okay? But it's pretty simple. I just go with the first charge because that one happens way more often than the other. Okay? So I say 2+, that's a 1-, CuCl2, 2 and 2, and I'm done. Okay? Everybody all right with that? So it's just a little thing. It comes up once in a while. You just have to know how to handle it. Okay, everybody come up and grab a Chromebook.